All right, this is a lab. There's actually four syntheses in this lab. We're just going to do synthesis one, procedure one. We're not doing two, three, and four. Normally, or two and three. I'm not sure how many there are. Normally, what we do is we read through the entire experiment, just so that we have an idea of the whole thing. Sometimes we have to prepare in advance for certain parts of this, so we would read through this here. And this is the preparation. When you look at this, what does this three waters mean at the end there? I can't annotate this, so I'm going to copy this and move it over into Word. Are those, we were talking about Werner. In Werner, we had ammonias, which would be analogous to waters of hydration. And originally, the thinking was that these ammonias get stuck in the little holes in the crystal lattice. But it turns out the ammonias weren't stuck in holes in the crystal lattice. Where were the ammonias located? They were actually bonded to the central metal ion, right? How about these waters? Are these aqua ligands, or are those waters of hydration stuck in the hole in the crystal lattice? What do you think? Stuck in the holes. How did you determine that these were not aqua ligands that were, coordinately, covalently bound or datedly bound to?
It's not within the complex.
Yeah, it's not within the complex. Do you see these waters are outside the complex? In fact, this chromium, what's the coordination number of this chromium? Can you tell by looking at this? 6. This is an octahedral compound. And that's because of this ligand, C2O4, 2 minus is called?
Bidentate.
Yeah, it's a bidentate ligand. And, it's oxalato or oxalate ion. When it acts as a ligand, it's called oxalato. And it's going to form an octahedral complex of 3 bidentate ligands. There's no room for the water. These waters have to go in the hole. So these are waters of hydration. And that's stuck in the solid crystal lattice. And so this is solid here. I didn't put the waters. We're going to do the equations, the chemical equations later, when we now analyze it. But I talked about the 3 reactions we're doing. Redox, what was it? Redox, acid base, and metathesis. So, just reading through this, slowed at 3.6 grams of potassium dichromate. Where did we leave off? Okay, let's draw that. Let's continue drawing that. I think I still have that. Let me see if I have that. Or maybe it crashed. I don't have it anymore. Oh, there it is. I do have that. All right. So we're talking, the way I'd like to have this is the lab notebook page. All right. What do we reserve the first 2 pages for? Table of contents. So leave those blank. So reserve first 2 pages for table of contents. I'll call it TOC for table of contents. So this experiment's going to start on third page. For the third page, what you can have is you can have outline the reactions that we're doing. I had already done that. And so now we're starting with the procedure. So this is kind of step one of the procedure. Step one of the procedure, I'm going to make a 10-gram suspension of oxalic acid monohydrate. Now these hydrates are stuck in the lattice, in holes in the lattice. This 10 grams in 20 milliliters of water. This is a suspension, meaning that not all the solid dissolves. It's kind of cloudy, pasty suspension. But what should happen to the suspension, it's like muddy water, but it's a white suspension because oxalic acid is white. What should happen is all the oxalic acid should dissolve with reaction of potassium dichromate. We should not see any oxalic acid remaining in this. We should get it all to dissolve. The reason is if we have undissolved oxalic acid, that is going to contaminate our final product. We don't want that to happen because our final product is also a solid. We have to slowly add this because why? Oxalic acid is so reactive, or potassium dichromate is so reactive. Yeah, because the dichromate is so reactive. Not only that, you want to warn yourself, dichromate is quite toxic. Oxalic acid is toxic too. Don't eat the stuff. It's not like vinegar or something like that where you can eat it. Oxalic acid is a chelating agent, and you don't want it to chelate, metals in your body that are needed for other functions. But anyway, going back to the dichromate, this stuff is hazardous, so be careful with this. And we add it slowly because dichromate is such a powerful oxidizer in the presence of acid. Well, we have acid present, and so this is the reaction that's going to happen. The orange-colored mixture should spontaneously warm up, almost to boiling. Okay, so orange-colored mixture, that means we need to know the color and form. So what we're going to do for observations here is we're going to write down how much we actually use. The procedure says use 3.6. We might have gotten 3.65 grams. But whatever amount you use, you write it here. If you make a mistake, then just cross it out with a line or two. Don't erase it. Don't use white out. Just cross it out and write the correct number there. If you overshoot it, no big deal. If you undershoot it, no big deal, as long as it's not by a large percentage. Okay, the other things we need to know is, unless you already know it, what does potassium dichromate look like? Did I already tell you?
It's yellow.
Chromate's yellow, dichromate is orange, and so this is going to be an orange solid. And most likely it's going to be a finely divided solid, so if you sneeze on it, you'll create a cloud of potassium dichromate. And if you create a cloud of potassium dichromate, you want to evacuate. You don't inhale this stuff. You saw, if you want to see the health data and the reactivity data, where do you look? What do you look for? What document do you look for? Safety data sheet. The safety data sheet is required by law to be included with the chemical. So every bottle of chemical we purchase can come with a hard copy of the safety data sheet, but you can find these online. Oxalic acid has some health risks too. There. A lot of organic acids aren't a big deal, like citric acid. People eat this stuff and eat lots of it. No problem there. So we add it slowly. Oxalic acid is white solid. The orange-colored mixture should spontaneously warm up almost to boiling as a vigorous evolution of gas commences. What happens sometimes is people dump all 3.6 grams at once. If you dump all 3.6 grams at once, then you know what it looks like? It looks like somebody put a Mentos in Diet Coke. Have you ever seen that? and then throw some Diet Coke, and then it sprays up hexavalent chromium all over their arms and hands. It's happened before. They just dump it in, and then they got this mad concoction that just oozes. And it effervesces quite a lot because it's generating a lot of CO2 gas. If it does spill on you, then make sure you wash it off. I usually use soap and water and then rinse for prolonged periods. But we add it slowly to prevent this. Okay, once the reaction has subsided, in about 15 minutes, dissolve 4.2 grams of potassium oxalate monohydrate in the hot green black liquid and heat to boiling for 10 minutes. So 4.2 grams. So we're going to let the reaction subside. And then we're going to add 4.2 grams here of potassium oxalate. And is that a hydrate? Let's see. Is that the hydrate? Yeah, monohydrate. If it's a hydrate, it weighs more. The molar mass is a little higher. So this is fewer moles. Versus the anhydrous doesn't have that water. And so we get more moles of oxalate. It's going to have a little less moles of oxalate because of the water mass. But it doesn't matter. We need to know what color this is. What color do you think this is? It's probably white. And so the procedure is over here. Observations, that's taken over here. So I write down what happened. What did it look like? The reaction was vigorous. So write down your observations over here. You just want a short picture of what was happening or what happened in words. Over here, 10 grams, you can put in the amount you actually use. Let's say you use 9.95 grams. Actually use, that's fine. This is actually a large excess. If we calculated it using some stoichiometry, then we need about 4 grams or 5 grams of oxalic acid. So we have way more than what we need. We're going to do the stoichiometry later. Here, we don't have to be as careful because this is a different type of reaction. What type of reaction are we looking for here? We want the oxalate to chelate the chromium-3, right? And so after this redox, we should have chromium-3 ion here, and we should be chelating it. So now we're on reaction 2. Up here, we're on reaction 1, which is the redox. This is the reaction 2, which is the chelating or the Lewis acid base. There. All right, and then we're going to heat this to boiling. So we add 4.2 grams and then heat to boiling. That's going to help the oxalate and oxalic acid to chelate the chromium-3. So we want to heat it for 10 minutes. Heat to boiling for 10 minutes. So this is what we're supposed to do. What we actually do might be slightly different. And so what you do is, let's say you heated it for 9 minutes and 30 seconds. You might write that here. Or let's say you heated it for about 12 minutes. This heating time is not so critical. Just around 10 minutes is enough. Sometimes it's critical. So if it's a little under or over, it doesn't really matter. Allow the beaker and its contents to cool to room temperature. Add about 10 milliliters of 95% ethanol with stirring into the cooled solution in the beaker. So we're going to heat to boiling for 10 minutes. We want to see, was there any color change? You know, what happened when we heated this to boiling for 10 minutes? That sort of stuff. Let's see. Got some pages in here. So here we're going to cool to room temperature. About room temperature. It could still be a little bit warm. And then we're going to add 10 milliliters of 95% ethanol. Ethanol is abbreviated ETOH, ethyl alcohol or ethanol, 10 milliliters. It says with stirring. I don't normally stir it. Further cool the beaker and its contents in ice. The cooled liquid should thicken with crystals. After cooling in ice for 15 to 20 minutes, let me go back to the lab. The crystals should be collected by filtration with suction using a Buchner funnel, see figure 3, and filter flask. Wash the crystals on the funnel with 3 10 milliliter portions of 50% aqueous ethanol, followed by 25 milliliters of 95% ethanol, and dry the product in air. Weigh the air-dried material and store it in a vial. You should obtain 9 grams of product. Calculate the theoretical yield. All right. Reactions of chromium-3 are slow, and your yield will be low if you work too fast. Anyway, what we're going to do is we're going to do this over 2 days. So we're actually going to stop here, cool it nice, and then stop for day 1. What I'm going to say is this. We're going to modify the procedure a little bit. This is minimum. Add more to maximize precipitate. So what we're doing is we're doing the metathesis, reaction 3, in which we want to precipitate out the solid. And the solid is going to precipitate out as a hydrate because there's water around. And so let me modify the equation I had up earlier. The equation was 3 potassiums, plus the trioxalate to chromium-3, or not chromium, chromate-3, plus 3 H2O liquids. And this is aqueous, and so we're going to add ethanol. And the more ethanol we add, the less soluble this should become, and the more we should precipitate out. And so we want to get a reasonable amount of this precipitate. This is going to be K3 CrOx 3.3H2O solid. And so we're going to make the solvent more ethanol-like and less water-like. The facilitate that. And so the more ethanol we add here, the better. The only thing we have to worry about is co-precipitation. Co-precipitation is we have excess oxalic acid, we have excess potassium oxalate. If we add too much ethanol, then we might get some white potassium oxalate and some white oxalic acid precipitating in addition to our black-green, these are green-black crystals. And so if you see some white precipitate too, then maybe it's a bit too much, to prevent that stuff from precipitating. We just want this. All right, to help, what we're going to do is we're going to cool this in an ice bath. And so I get a bigger beaker. We started, this is a 250, so maybe I'll get a 400 or 600 milliliter beaker and then put in ice water here. Not just ice. Ice doesn't conduct heat very well. Ice water is a much better conductor of heat. And so we want ice water to cool it down. And typically, as it gets colder, the solubility decreases and we should get more precipitate. Okay. So this is the end of day one. So you want to have this prepared in your notebook. All right, any questions on this? All right, try to get the lab to download off Canvas. Hopefully it works. Let's go back to chapter 13. Were there any other questions? Chelating. Basically, we have chelating is we have oxalate. Ions. We need the oxalate ions to attack the chromium 3. So we have 2 donor atoms here. And that'll be one bidentate ligand. Usually we heat this up, we'll get more collisions, and the reaction should proceed faster. Normally when you heat things up, you get more collisions, more energy, and typically that helps speed up things. We can fit 3 of these oxalates around chromium. All right, any other questions? No? So thermodynamics is involved and a bit complicated. There are a lot of equations and a lot of relationships, and you should know them, like the difference between internal energy and enthalpy. When do you use internal energy? When do you use enthalpy? This kind of stuff. And so that's good stuff to review. But what I'm going to do is I'm going to just focus on really what we need to know for Chapter 13 and Chem 1B. Why we want to spend all this time looking at these relationships is we want to better quantitate the driving force. Did I talk about the second law and the third law already of thermodynamics? No? I did the second. Does anybody have the third law written? What did I say about the second law of thermodynamics?
I think you only said spontaneous driving force.
That's it? All right, so I ran out of time there. So we have the laws of thermo. And the first law we already talked about. The second law. The second law talks about spontaneous processes or spontaneous reactions. And so what is spontaneous? Normally something that's spontaneous has what I call a driving force. Some people don't call it this, but it's got to have some kind of driving force. So there's a driving force for a pen to fall down. Let's say I'm holding this pen up here and I accidentally let go of it, it's going to fall down. What is that driving force for a pen to fall down? Well, it's, what it is going from higher energy, we call this higher gravitational potential energy, to lower energy. Nature things tend to lower energy, so that's spontaneous. However, would it spontaneously fall up? No, because there we're going from lower energy to higher energy. So we don't expect it to fall up, we expect it to fall down. And that's what we see in nature. And so what we're looking at is spontaneous. If it's spontaneous, there must be some driving force, like energy, going from higher energy to lower energy. And so what we're going to do is we're going to look at this more quantitatively. Spontaneous means that there must be some driving force, and what we want to do is we want to quantitate that driving force. Because right now, our driving force is, does it precipitate? If it precipitates, then yes. Are we going from stronger to weaker? Then yes. That type of stuff. But some driving forces aren't so strong. So like in Chem 1A, we had two scenarios. One, there's no reaction. No reaction means, yeah, it's going up, and it's going up quite a lot. So we see no reaction here. We're going from low energy to high energy. Or there's driving force. We have driving force for reaction. We're going from here down to here. And so we expect either 0% reaction or 100% reaction. But in reality, we could have partial reaction. And in Chem 1B, we're going to look at scenarios like that. That is, maybe it's like this, where maybe the climb isn't as high. And so I might have partial reaction here. Yeah, we're going from lower to higher, but when we look at the population of molecules here, let's say, they don't all have the same energy. In fact, if I look at the population of molecules here, I'm going to see a distribution of energies, and the distribution is called, what type of distribution is that called? Yeah. You guys can hear that? The Maxwell-Boltzmann distribution. In the Maxwell-Boltzmann distribution, there's a small population of molecules that have higher energy, and those can make it up here. So even though we might say, we're going from lower to higher, that is weaker to stronger or whatever, it still could happen. It still could happen because of the population that has a bit more energy that can make it up that hill. But if that hill is too big, then there's a negligible or zero population that can make it up that hill. The same thing here. Everybody can make it down the hill. Even the lowest of energy particles can fall down the hill. But what might happen in a scenario like this is, yeah, everybody can make it down this hill. And so everybody makes it down the hill, but not everybody stays at the bottom of the hill. Because, again, we're going to have this distribution, and that means some of them are bored, let's say. Some are bored down here, and they want to climb back up. And so if they climb back up, then we end up repopulating the initial state. And so what we end up with is two scenarios where we'll have partial reaction. And in Chem 1B, we deal with these scenarios where we have partial reaction. Well, partial reaction, we got to look at the differences in driving force. So, for example, here, the driving force isn't so large. And over here, the driving force isn't so forbidding. Here, there's no reaction. The driving force being going back up the hill, or that's not really the driving, but driving force would be reversed. And so partial reaction. So we're going to look at the driving force more quantitatively in Chem 1b. In order to look at the driving force more quantitatively in Chem 1b, we need the second law of thermodynamics. The second law of thermodynamics, in the first law, we learned about the symbols Q, W, U, H. Was that it? Yeah. In the second law, we're going to learn about the symbols S and G. S, did I talk about that already? S is the symbol for what? S is the symbol for something called entropy. Entropy is a measure of disorder. So the higher the S, the more disorder there is. Or constraints, too. G is called the Gibbs energy. So now we have these energies, the internal energy, the enthalpy, and the Gibbs. What's the difference between these three? What's the difference between these two? Well, we need to go back and look at the difference between these two. Chem 1a. But we got to differentiate that from the Gibbs energy next. And so now with all these energies, things start to get confusing. Now, it'd be easiest if there's just one energy, like the gravitational potential energy, and things fall down. Did I talk about absolute enthalpies, absolute internal energies, and absolute entropies? Yeah? Do we measure absolute internal energies? Or absolute enthalpies? No. Because the 0 point is not so certain. However, we do measure absolute entropies. So entropy calculations are fairly straightforward, and that's because of the third law of thermodynamics. What does the third law of thermodynamics state? The entropy of a perfect crystal at 0 Kelvin is 0. That gives us an absolute 0. It's like 0 Kelvin. 0 Kelvin is absolute 0, whereas 0 Celsius is not. 0 Celsius is called an arbitrary 0. It's not an absolute 0. Well, we have the same thing for entropy. If we had a perfect crystal, then everything is in its proper place. There is no disorder. And if it's at 0 Kelvin, there's no movement either. So it's just frozen perfectly. And so that would be the lowest entropy we can have. Just like the lowest temperature we can have is nothing moves. There's no kinetic energy, therefore it's 0. And what that means is we can do simple calculation. So for example, if I want delta S is simple. Delta S is S final minus S initial. We just take the absolute entropy final minus the absolute entropy initial. Whereas if I want delta H or delta U, I can't do that because we don't calculate the absolute internal energies and absolute enthalpies. And so the third law allows us to determine the absolute entropies. And we'll talk about how that's done later. And so we're going to be using this stuff in a little bit. And so how do we quantitate the driving force? Well, we can use laws of thermodynamics to do that. So why do we want to quantitate the driving force? Why we want to quantitate the driving force is in order to do Chem 1b stoichiometry. Chem 1a stoichiometry is simple. Chem 1a stoichiometry is there's no driving force. This hill's too big. Nobody's going to make it. And so Chem 1a is either black or white. In this case, here, it's going to be 0% reaction. If it's 0% reaction, we just say NR. So the stoichiometry is easy. Nothing happened. Or the trip downhill is so steep and so long that nobody can make it back up. That's 100% reaction. And so in Chem 1a, it's either 0 or 100. Whereas in Chem 1b, it's going to be anywhere between 0% and 100%. And then everything in between. So these are what we call partial reactions. This is Chem 1b. And this is something we want to do. We want to do stoichiometry here. So to give you an example, we know that weak acids are weak electrolytes. So this would be an example of Chem 1b. Weak acids are weak electrolytes. Weak acids are weak electrolytes. Weak electrolytes partially ionize / hydrolyze. So let's take an example of weak acid, acetic acid. And acetic acid is going to partially ionize or hydrolyze into the ion. So the question is what is the percent? Well, it's not 0%, and it's not 100%. The percentage is in between 0 and 100%. I've done this calculation before, and it's like 99.9% unreacted, so it's only 0.1% hydrolyzed or ionized. But how did I figure that out, and how do I get that number? So for Chem 1b stoichiometry, we have two approaches to this. The first approach is empirical, through observations, experimental observations. And this empirical approach is primarily in like chapter 15, etc. Or the other way we can do Chem 1b stoichiometry is through more of a theoretical approach. Which would be chapter 13. Etc. I mean, there's some overlap. And so we can take a more empirical approach or a more theoretical approach. I don't like the order. I'd like to start off with the empirical approach first and then do the theoretical approach. And so what that means is I'm going to jump to chapter 15 for a little bit. So let's go ahead and jump over to chapter 15. Do you have a hypothesis about how to do Chem 1B stoichiometry? Can you tell me how to figure out the driving force and how to figure out how much reaction we're going to have? For example, strong acids is easy. Strong acids are strong electrolytes, ionize 100%. So we'll get 100% hydrolysis or ionization. But let's pick out some weak acids. What's the strongest weak acid on that chart up there? The strongest weak acid on that chart. It is. It's oxalic acid. And oxalic acid is a weak acid, so it doesn't ionize 100%. So what is the percent ionization of oxalic acid? Can you come up with a hypothesis for me? Well, that's the strongest of the weak acids. We can go to a weaker weak acid like acetic acid. I can tell you what the percent ionization on acetic acid is. It's like less than 0.1%. We can measure it, you know. We can measure the percent ionization. It's pretty easy to measure, actually. I'll tell you how to measure it in a minute. But do we start off science with a hypothesis? Well, maybe in some fields, some fields they say the scientific method begins with a hypothesis, but can you come up with a hypothesis for me? How we're going to predict what the percent reaction is for this? Not easy. And so this is why the scientific method that I proposed, wrote up on the board. What was the scientific method I wrote up on the board? The steps. Let's have that. We start off with observations, yes. Not quite the laws yet. Not quite the predictions. We use laws for making predictions. We aren't predicting anything. We start off with, predicting is hard, right? Predict the percentage ionization for bicarbonate ion for me. So we can't start off with prediction unless we have something more. We start off with observations and then do what? Did you guys write it down? I think it was day 1 or day 2. It's like if you do like the same, some things you don't notice. Like if you take the same path every day, you start to notice, different things. Maybe sometimes if you walk the same path, it's not the same each time. Sometimes you notice little things that are different, right? And those stand out more because the other stuff, it looks the same, so you notice the new things more. That's the same thing in science. You take the same path every day, and then you start to notice things, little things that you might not have noticed before, details. Or you make connections, Does somebody have it? Well, let me go back to this. I thought this was more clear. This is approaching it from two sides of the scientific method. When we look at the scientific method, one side begins empirical. Empirical observations are just experimental observations. And so we start off observations, and then we look for what in the scientific method? patterns. We look for patterns or trends. If we find some patterns or trends and we can define those mathematically, then we have a law. So they're taking observations of gases and they notice certain patterns and trends with gases and they come up with the gas laws. And then we can use the gas laws to make predictions. So we can use the laws to make predictions. And so, and then we combine those gas laws to make the ideal gas law. So we have the ideal gas law, PV equals nRT. But then the question comes up, why does it take that form? That is, I have a law, it's PV equals nRT. I can use that law to make predictions. I can calculate, the volume given this and that. I can calculate the pressure. So I have the law, I can make some predictions, but I want to understand it at a more fundamental level. Like, why does it have this form, PV equals nRT? Where does it come from? How can I relate that to atoms and molecules and whatnot? And so next comes the hypothesis. The hypothesis is trying to get a deeper understanding of what that law is all about. Hypothesis. So the hypothesis for this law is there are things called atoms and molecules, and these are in motion, and we have that. And eventually, then we can collectively combine this into a theory. Do you guys recall this? Stuff. Theory. So when we're doing our stoichiometry, we have two approaches we can do. We can take it from the observational, this is the experimental side of things, or we can start off with theory and then try to derive our Chem 1B stoichiometry from a more theoretical point of view. Physicists are doing this all the time, like at the Large Hadron Collider in Europe. There are two camps of physicists. You have the theoretical physicists, and then you have the experimental physicists. And they meet in the middle, and when they meet in the middle, it should meet at the same point. But sometimes there's a mismatch between what theory predicts and the observations. So what we're going to do is we're just going to look at the observations. We're not going to try to predict. That would be too difficult, wouldn't it, to predict what the percentage ionization is for all the weak acids? Yeah, I think so. That would be predict. So let's take a look at a reaction. And so chapter 15, we're going to take the empirical approach. To Chem 1B stoichiometry. And eventually this converges where we take both the empirical and the theoretical. And we just use all the tools available. And so we're going to take a look at this reaction, which is going to be copper 2 ions reacting with tin 2 ions. We'll need 2 copper 2s because what we're going to do is tin normally is a really good reducing agent, even with a 2+ charge. It doesn't hold on to its electrons too tightly. And the coppers can oxidize it. Normally when copper 2 oxidizes, it wants 2 electrons to form copper metal. But in this reaction, each copper is only going to gain 1 electron here, and we're going to end up forming tin 4. Tin 4 is fairly high charge, but it's not terribly unstable. That is a powerful oxidizer. So is there a driving force for this reaction? So let's just compare. Copper 2 is the oxidizer in the forward direction. What's the oxidizer in the reverse direction? Tin 4 or copper 1? Tin 4. This is oxidizer. Now, do you have your chart? Can you tell me which is the stronger oxidizer, copper 2 or tin 4? Copper 2. Okay. This is stronger. This is weaker. So in Chem 1A, we'd say that there's driving force present. For Chem 1A, driving force is present, check. Therefore, we expect 100% reaction. In Chem 1B, we'd start to worry. How big is that driving force? Is copper 2 a lot stronger than tin 4 or a little bit stronger than tin 4?
Only a little bit stronger.
It's only a little bit stronger. If it's only a little bit stronger, then is there a chance that some of these can go backwards, can go back up the hill? And so this is a downhill reaction. But in Chem 1B, we start to worry about, will the entire population stay at the bottom of the hill? Or do some of these in that population have enough energy to climb back up? You know, they're bored. They don't want to stay at the bottom of the hill. Everybody else wants to stay at the bottom of the hill, but some, you know, this is like when you go on trips in high school or something, there are people running around, but most people are just hanging out, you know, something like that. So it's the same thing here. Do we have to worry about these ones that might be able to climb back up the hill? That is, this reaction is reversible. And so probably do you have a hypothesis? Can you predict it? Not really. Let's just go ahead and just take our observations. Our observations are this. In Chem 1B stoichiometry, we always set up this type of table. Chem 1B stoichiometry, we make something called the ICE table. ICE. The ICE table stands for initial. The other odd thing about Chem 1B stoichiometry is we don't use moles or grams or whatever else. We usually use molarity. So what I'm going to do is I'm going to put 1.100 molar copper 2. And in the same solution, I'm going to make the tin 2 0.100 molar. So I have a mixture. This mixture contains both copper and tin at 0.100 molar. And then there's no product initially because I'm not going to put any copper 1 or any tin 4 in there. So that's 0 and 0 molar. So that's my initial. And then I'm just going to let it react. And when it reacts, there's going to be a change. Until finally I hit what we call equilibrium. So initially all of them are up here. Then there's going to be a change. They're all going to fall downhill. But then we're going to reach some state of equilibrium because not all of them stay downhill. Some of them will go back uphill. And so what I need to know is I need to know, you know, how many go back uphill. But eventually what will happen is I'll have some go back uphill, but then this will be compensated for by ones going downhill, and eventually I'll have this. In a dynamic equilibrium, the rate of change in the forward direction, that is downhill, is equal to the rate of change in the reverse direction. These two rates are equal. So the number of particles falling down is equal to the number of particles climbing back up. And what I've reached is a state of dynamic equilibrium. Dynamic equilibrium is a condition where the population down here doesn't change and the population up here doesn't change. And so that's static, that's equilibrium. But it's dynamic because there's constant particles falling down and constant particles going back up. So in Chem 1A, we'd expect, what's the limiting reagent here? Copper 2 is the limiting reagent. And so we're going to consume all the limiting reagent, so we'll be left with 0. And for every copper, I need half as much tin. So I'm only going to consume half of this. And so I'll be left over with half of that, and then I'll figure out what the theoretical yield is over here. That would be Chem 1A, since there's a driving force. But in Chem 1B, we could have this partial reaction occur. That is incomplete reaction. Yeah. And so I'm not going to hypothesize. We're just going to look at what happens. So we'll let this reaction go and go and go. And over time, it stops changing. And when it stops changing, then the reaction is done. And so let me get the data for this reaction. I need to get the data here. The data is from our book. Chapter 15. So somebody did this experiment, not me. So here's the data. This is experiment 1. And so at the end of this, I'm going to have 0.036, 68, 64, 32. I'll quickly forget those, but 0.036, 0.068, 0.032, 0.064, thank you. 64 and 32? Thanks. Let me clean that up. So in Chem 1A, we would expect to have a 100% reaction of the limiting reagent, which we didn't. What was the change? Oh, so this is after everything's been stabilized. So after everything's been stabilized, this is the population we end up with, the distribution. So let's see what the net change was. Over here, we lost some. How much did we lose? This is going to be minus 0. Can you see how much we lost? 6.4. So we started off with 100, we lost 64, we were left over with 36. And so this comes out to a 64% reaction. So 64% made it down here, and then a 34% climbed back up here, or 36% climbed back up here. Okay. Could you have predicted that? I don't think so. So we start off with observations. In science, we start off with observations. It's too hard to predict stuff. What was the change for the tin? How much did we lose? 0.032. So we started off with 100, we lost 32. If we start off with 100 and lose 32, that's a 32% reaction. This one's trickier because this is the excess reagent. And so the percent reaction is usually based on the limiting reagent, 64% reaction here. But we lost half as much tin. Does that make sense? Shouldn't we lose the same percentage? And the answer is no, because you see we need twice as much copper than tin. And so we're going to lose twice as much than tin. And the situation goes like this. If we lose 0.064, does that disappear? No, we have conservation of atoms. So the copper can't disappear. So I know what the gain. So if this is minus 0.064 here, this has got to be plus 0.064 here. Because the copper atoms can't disappear. And if this is minus 0.032 here, this has got to be plus 0.032 here. Because of the stoichiometric ratio. And the stoichiometric ratio holds regardless if we're doing Chem 1A stoichiometry or Chem 1B stoichiometry, because we need twice as much copper as tin. If we need twice as much copper as tin, then what we call this minus 2x. X we don't know, X is hard to predict because X is how much, we're actually losing. What is the percent? Are we going to have 100%, 90%, 0% reaction? What is the percent reaction going to be? That's hard to predict. But we can predict that if we have 2x for copper, then tin will be x, half as much. We usually keep x being the smaller, or the smallest coefficient. And so tin being 1, that would be x. And the copper would be 2x because it's twice as much. And so therefore x is 0.032. And 2x is 0.064. Over here, this is going to be plus 2x, and this is going to be plus x. So given one of these, we can figure out the other three just using straight stoichiometry, Chem 1A style stoichiometry, conservation of atoms. But how do we figure out what x is? Well, we just figured it out experimentally. We figured it out using empirical observations. So that we see that we got 64% reaction here, or 32% reaction with tin, too. And so now I have an idea of what's going on here. So this is experiment 1. Okay. I'm going to jump to experiment 3. Maybe not. So we got our copper 2 plus plus tin 2 plus. We need two of these. It's going to form two copper 1 plus and a tin 4 plus. This time we're going to start off differently. I'm going to start off with 0.100 molar copper 2, 0.100 molar tin 2. And in this case, I'm going to put some product in there too. 0.100 molar copper plus and 0.100 molar tin 4 plus. And so I'm just going to add those in there and then see what happens. Let's see if we can predict it now. So we had 64% reaction? So what do you predict here? Minus 0.064, right? Minus 0.064. And I predict we're going to end up with 0.036 molar here. Same thing. And then this one will be minus 0.032. I need half as much tin, so minus 0.032. And I predict this will be 0.068. Is that right? And then what would this be? The copper 1 would be plus 0.064. Atoms aren't created nor destroyed, so if I lose 0.064 copper on the left, I have to gain 0.064 copper on the right. This copper didn't disappear, really. It's changed. So this is going to be 0.164 molar. And then the tin, I'm going to gain how much? Plus 0.032. And so my prediction is I'm going to get 0.132 molar. Okay. So I'm making a prediction based on percent reaction that we saw. And so I'm using the previous observation to look at this. And so this is my, I guess, my theoretical prediction, although I don't really have a fundamental understanding of what's going on. I just see a pattern, and I'm just trying to use that pattern to make a prediction. I'm going to have to compare this with the experimental data. And so let's take a look at the experimental data. This is experiment 3 from our book. And so if we look at experiment 3 from our book here, these are the numbers down here. So the copper comes out to 0.0922. So this goes to 0.0922 molar. I'd like to go 3 decimal places because that keeps this at 100. So I'm going to go 92C2. That means 92.2% remains unreacted. And how much did I actually lose then? The amount that I actually lost is very small. The amount I actually lost is 0.0078 molar. Is that right? Yeah. Yeah, and if I start off with 100 and I lose 7.8 of that, that's only a 7.8% reaction. That's way less than my 65% or 64% reaction that I predicted. This is nowhere near 64%. If I lose 0.078 over here, I can predict the others. How much am I going to lose over here? Yes, I should lose 0.0039 here. And if I lose that much, then I'm going to end up with 0.0961. Is that right? Yeah. Let's see, is that how much we got? Well, according to Chem 1A stoichiometry, that should be how much we got. According to observation, is that how much we got? 0.0961. So that's correct. The first one we had to determine, the rest we can figure out. How about over here? How much copper 1 am I going to gain? This is going to be plus 0.0078. And so what that means is I'm going to have, or I should have, 0.1078 molar. Is that how much we ended up with in the experiment? So yeah, I have 0.1078. So the stoichiometry is holding. It's just I didn't know the extent, you know. How could I have predicted the percent reaction was so small? Percent reaction was only 7.8%, but once I know what that percent reaction here, then I can figure out all the rest, because all the rest is going to follow standard stoichiometry. How about 10? How much am I going to gain here? So this is going to be plus 0.0039, which is going to give me altogether 1039 molar. Is that what we got experimentally? Yeah, that's what we got experimentally, 0.1039. But the problem is how could I have predicted? How could I have predicted this 7.8% reaction initially? It's nowhere near experiment 1 with 64% reaction. So are you ready to make a hypothesis? Now I think we need more observations, right? And so let's try another set of observations and see if this experiment might help us. So we're going to go to experiment 2. 2 copper 2s plus a tin 2 is going to yield 2 copper 1 and a tin 4. In this experiment, what we're going to do is we're going to go 0 molar here, 0 molar here, and then we're going to go 0.100 molar here and 0.100 molar here. There's going to be a change, and then we're going to end up at equilibrium. And so maybe we don't even want to guess here. I'm not even going to guess. Let's just go ahead and write down all the equilibrium values for experiment 2. So the first one's 0.0567 and then 0.0283. 567 and 283. So I'll write that here. 0.0567 and 0.0283. And the second two are going to be 0.0433 and 0.0717. 433 and 717. 0.0433 and 0.0717. Here. Now, this stoichiometry has to hold. So whatever I lose here, this is going to be called minus 2x. And whatever I lose here is going to be called minus x due to the stoichiometry, 2, 1. And that means I'm over here, I'm going to gain x. And over here, I'm going to gain 2x. In other words, this is going to go back up the hill. In Chem 1A, we'd say there's no driving force to go back up the hill, but we already know some of these can make it back up the hill. It's just how much is going to make it back up the hill. And so let's see, our limiting reagent here, again, is copper. So let's figure out what 2x is. So how much did we lose here? This is minus 0.0567 molar. And so in other words, this is 56.7% made it back up the hill. 56.7%, that means less than 50% remain at the bottom. How could that be? Is this making sense to you at all? I don't know. Oh, and then over here, there's going to be half as much. Half as much is going to be minus 0.0, what is it? 283 molar. And so this is our 2x, so this is going to be plus 0.0567, and this is going to be plus 0.0283 molar here. So do you have it figured out now? No. All three percentages are different. Anyway, we were out of time, so I'll stop here. So how many more observations do we need?